Let's see now nth order linear differential equation with constant coefficients. As we know, differential equations are those which has derivatives. Derivative of dependent variable with respect to independent variable. So in this specific type of differential equation, which is nth order. So nth order stands for order of the derivative. So the maximum derivative term in this equation is n. Constant coefficients. Coefficients of these derivatives are constants. Coefficients of these derivative terms are constant. And linear stands for degree of this equation, or we can say there are no two derivatives multiplied, there is no dependent variable and derivatives are multiplied. Non-derivative term, single term of y is there. This equal to f of x. This is general form of nth order linear differential equation with constant coefficients. Now we have to solve this equation. So before solving this, let's define one operator d. D stands for derivative with respect to x. Similar to addition, subtraction, multiplication operator, this is a derivative operator d. So whatever the power of this d stands for order of derivative. Stands for order of derivative. It obeys rules of algebra. For example, d raised to m divided by d raised to n. We can write this as d raised to m minus n. D raised to m into d raised to n. We can write this as d raised to m plus n and so on. When we solve problems, we'll further see the algebra of operator d. So let's write this equation using this operator d. Let's write this nth order equation using operator d. So in first term, we have nth order derivative operating on y. Second term, n minus 1 order derivative. Third term, n minus 2, so on. Last term, there is no derivative, so as it is y is equal to f of x. As we can see on left hand side, there is operator operating on y. So we can take y common here. Taking y common because each term is operating on y. So this bracket is nothing but a polynomial in D. This bracket is nothing but a polynomial in D. Let's write this in another notation. Suppose we write this as phi of D. A polynomial of D operates on a y is equal to f of x. So even this can be a general form of nth order. Nth order, if the degree of this polynomial is nth order linear differential equation with constant coefficient. Now we have to solve this equation. How to solve? Derivatives of y is equal to f of x. So solution of this equation is going to be y is equal to some function of x. How to find this solution? To find this solution, two parts. Y is equal to yc plus yp. We call yc as complementary function. Complementary function, and this yp is called as a particular integral. It's called as a particular integral. Now let's see how to find these two parts. So let's find first part, that is complementary function. To find complementary function, we have to solve this equation phi of d of y is equal to 0. Complementary function is solution of this equation. Now how to solve this equation? To solve this equation, we have to equate this polynomial phi of d is equal to 0. This equation is called as auxiliary equation. Solution of this equation depends on roots of or values of d. Roots of phi of d is equal to 0. Now when say roots of a polynomial, the roots can be real and roots can be imaginary. Also, roots can be same or repeated, or roots can be different. So depending upon these nature of roots, we get different cases of complementary function. So let's see one by one. Case 1. Roots are real and different. Roots are real and different. For example, 3 roots are there. We get, after solving auxiliary equation, suppose we get 3 values of d, m1, m2 and m3. Then corresponding CF we write as C1 e raised to m1x, C2 e raised to m2x, C3 e raised to m3x. That is, for each root we are adding similar term. Constant multiplied by exponential term, and to the power of exponential term, root multiplied by the variable of the solution. Now, if we get 4 roots, suppose the roots are a, b, c and d. Then corresponding CF, C1 e raised to a into x, C2 e raised to b into x, C3 e raised to c into x and C4 e raised to d into x. So whatever the number of roots are there in the solution, we get that many number of constants. These are constants of integration actually. Constants in the CF. So you can verify this while checking your answer. So whatever the degree of auxiliary equation, we get that many number of roots and we get that many number of constants in the CF. So this is first case, if the roots are real and different. Now let's see the second case. Roots are real and same. Let the auxiliary equation has degree 2. So we get 2 roots. Suppose both the roots are m and n. Since the roots are real, we are going to add similar term, similar exponential term to CF. But for repeated part, we get C1x plus C2 e raised to mx. Now, suppose there are 3 same roots of kind m, m and n. That is, m value is repeated 3 times. Then corresponding CF, C1x square, C2x plus C3 e raised to mx. Now the polynomial starts with degree 2. C1x square plus C2x plus C3 e raised to mx. If 4 roots are there and all the 4 roots are A and A, then corresponding CF C1 x cube C1 x cube C2 x square C3x plus C4 e raised to A into x. This is second case. Let's see next case, case 3. For real roots, there are two cases, real roots different and real roots repeated. Let's check for imaginary roots now. Case 3. If imaginary root appears, imaginary roots. If imaginary root appear, it appear always in a pair. It appear always in a pair. So for this one pair, CF is e raised to alpha x C1 cos beta x plus C2 sin beta x. For this one pair that is two roots, so two constants C1 and C2. Suppose, for example, 2 plus 3r is a one imaginary pair. Corresponding CF e raised to 2x C1 cos 3x plus C2 sin 3x. So whenever imaginary root appear, it appears in a pair. Now, next case is going to be imaginary roots repeated. So whenever repeated imaginary case is there, the pair is repeated. You'll never get 3 imaginary roots. You'll either get 2 or 4 or multiple of 2, because imaginary roots gets repeated in pair. Suppose this pair is repeated twice. We get a pair of 2 pairs of such roots. That is, there are 4 number of roots now. So corresponding CF e raised to alpha x C1 x plus C2 C1 x plus C2 cos beta x C3x plus C4 sin beta x. This is corresponding CF for repeated imaginary roots. Suppose this pair is repeated 3 times, then corresponding CF e raised to alpha x C1x square plus C2x plus C3 cos beta x plus C4x square C5x plus C6 sin beta x. 3 pairs, that is 6 roots, 6 constants are there in the CF. So this is first part of the solution, that is a complex.